Okay, Chapter 5, Section 1, Areas and Distances. Okay, we're going to begin this section with something called the area problem. So the area problem is going to be, just like it sounds, find the area of a given shape. So for instance, we might be given a curvature y equals to f of x, right? So that's this curvy part right over there. And we might be asked to find the area shaded in blue, everything shaded in blue, which is the area trapped below the line y, or the curvature y equals to f of x, above the x-axis, to the right of the vertical line x equals to a, and to the left of the line x equals to b. So the question might be asked this way: find the area of the region S that lies under the curve y equals to f of x from A to B. Right? So that statement refers to this blue shaded region here. And then another notation for that S, the blue shaded region, is this. S equals to all ordered pairs x comma y, and then this bar right here reads such that, and then we have a condition for the x and we have a condition for the y. So all ordered pairs x and y such that the x is trapped between a and b inclusive, so all the x values or any values here along the x-axis between a and b, and y on the other hand is any value that is strictly greater than or equal to 0 but less than or equal to f of x, right? So for the x-axis, the a and the b are two constants, right? So that just stays still. But for the y, the 0 is constant, but the upper boundary of the y is a function itself. So this is sort of moving as a function of x. Okay, well, we've dealt with lots of questions involving area before. Of course, back in geometry class, we learned that the area of a rectangle is famously a multiplication of the length times the width, so L times W. And then the area of a given triangle is equal to 1/2 base times height. Of course, we know the area of a circle, and we can also use those three basic shapes to find some more complicated shapes by breaking it up and turn it into a summation of either triangles, like in this picture here, or maybe rectangles and triangles, or circles or half circles and triangles, right? So we can go pretty far with that. However, this situation is different. So far, all the work we've done before you've gotten to calculus, none of that has prepared you to be able to find the area when one of the sides is curvy like this, right? We always have either a circle, a nice perfect circle, or some version of a circle, or shapes that have straight edges. But here we have our first experience dealing with something that has a curvy edge to it. And the curvy edge, which will be defined by some function f of x. Okay, so let's do an example. Okay, use rectangles to estimate the area under the parabola y equals to x squared plus 1 from 0 to 4. Okay, so the from 0 to 4 refers to the input variable x, so as x ranges from 0 to 4. So this refers to x goes from 0 to x equals to 4. That's what this from 0 to 4 refers to. And then we have our function y equals to x squared plus 1. Okay, so let's use a technology to graph this and get a good idea of what area we would like to estimate. Okay, so I'm using this free online applet right over here. You're welcome to go to it if you want to play with this yourself. I'll explain all these bells and whistle things over here in a little bit, but for now, all that I'm going to point out is that I've typed in the equation we're working with right here, x squared plus 1, and so that's what this is, x squared plus 1. It's a parabola that's been shifted up by 1 unit. So of course, this right here is the point 0, 1. And we're interested in going from 1 to 4. I'm sorry, from 0 to 4. 0, 1, 2, 3, 4. So we want to go from 0 to 4. and we want to find the area underneath the curvature trapped between to the right of the y-axis, to the left of the vertical line x equals to 4, above the x-axis but below this curvature. So let's put this here from 0 to 4, and it would be this gray shaded region. That's what we're trying to approximate. Okay, so it's the area to the right of the line, the vertical line, x equals to 0, to the left of the vertical line, x equals to 4, above the x-axis but below this curvature. That's where we're trying to approximate right there. Okay, so we're saying that the area of this giant rectangle, going out like this, is my very first approximation, my very first guess for the shaded gray region. Obviously, a terrible approximation, as you can see, but we're going to use it to establish a pattern, and from that pattern, we'll get an even better approximation. So the area, we're going to say, is approximately equal to this red rectangle. Now, the base of the rectangle is going to be this distance here, which goes from 0 to 4. So we're going to say that this is delta x, and delta x is equal to 4 minus 0 divided by 1, because there's one rectangle. Again, I'm writing it this way because we want to establish a pattern. And then the height is equal to the value of our function evaluated at 4. Right? This point right there is the point 4 comma f of 4, which we know is 4 comma 17. Good. So that area, this big rectangle, is approximately equal to 4, which is the base, times the height, and the height being f of 4. So the area is approximately equal to 4 times 4 squared plus 1, which means that that area is approximately equal to 4 times 17. 4 times 17. Or that area is equal to, approximately equal to, 68. Okay, so let's try another. Okay, so here's our first approximation of the area, a terrible approximation. And notice that for the base of the rectangle starts from 0 to 4, the region we want to cover for x, and then the height went all the way up to a value, a point that's on the curvature, y equals to x squared plus 1. But in particular, we used the rightmost point, the x equals to 4 value, to establish that height up there. That's why we call this r sub 1. R sub 1. So r represents right, so it's the rightmost point, and the 1 indicating that we tried one rectangle. Okay, so 4 times f of 4 is r sub 1. All right, well, we could also have tried an approximation that works with the left endpoint. So let me insert that. I'm going to get rid of some of these bars here, and then let's put it in green. Okay, we're going to start again in the same spot there, and we're going to go out to this value, and then we're going to go up to there. So now this green box is another approximation. This time we have the same base from 0 to 4, but the height is being determined by the leftmost endpoint when x equals to 0. So this is just another approximation of that area. So we'll say that the area is approximately equal to, the multiplication of this 4, right? It's still the base, which is 4, delta x, times f of 0 this time. We're using the left endpoint. So we call that L sub 1, right? Because we're using the left endpoint to establish the left endpoint along, when we think of the base of the rectangle, we're going to take the left endpoint and we're going to use that to establish the height of the rectangle. So then this becomes that the area is approximately equal to 4 times 0 squared plus 1. So 0 squared is 0 plus 1 is 1. So we're going to get that this area has an approximation of 4 times 1, which just equals to 4, and that is our L sub 1 value. Okay, so obviously the red one, when we used the red one to approximate our area, that was this whole thing over here like this. Clearly from the picture you can tell that we're way off. That red one is way too big. The answer of 68, the area of that whole red rectangle, is way, way bigger than the actual area we're interested, which is that shaded gray region. On the other hand, the area in green, which is just going to be this 4, is way less. So what we've established is that the real answer, the area that we're interested in, is less than the 68, but greater than the 4. Right? And then in terms of these R and L values, the left sub 1 less than area less than R sub 1. Okay, so the area is clearly somewhere between the two. Good. It's not always going to be the case that the area is trapped this way, that the left approximation is always to the left below the area and the right approximation is always to the right. It's not always going to be the case. We'll see that in some cases it's the other way around, but it's certainly the case in this picture the way we have it here. Okay, well, let's move on to a better approximation. We're just trying to establish a pattern. Clearly this is way off. We want to do a better approximation, and to do a better approximation we got to include more rectangles. Okay, so now let's try doing this with 2 rectangles. Okay, so remember the curvature is the equation y equals to x squared plus 1, and we know that this up here goes up to 17, and that leads to this point. That's the result of inputting a 4. When we input a 0, it goes up to 1. So let's put in 2 rectangles. So let's think first of all about the width of the rectangles. So the width is going to go from, let's put a 0 in there. We're going to call that delta x. So delta x, which is the width of the rectangles, the change in the x, delta x, is going to be equal to 4 minus 0 divided by 2. Remember earlier it was 4 minus 0 divided by 1 because it was going to be 1 rectangle. Now we have 2. So this is going to be equal to 4 divided by 2, which is equal to 2. This lets me know that the width of the rectangles is a width of 2. So if we start at 0 and we're going to go width of 2 for each rectangle, means that this is where they're going to stop, at 2. Where the width from there to there, this width, is going to be delta x. Delta x equals to 2. And, well, this is going to be the exact same delta x as well. Good. Okay, so now it's going to be kind of messy. Let's get rid of this thing here. Put it underneath. So this is my delta x, which is a width of 2. And this is my delta x, which is a width of 2 as well. Okay, so they're the same width. So let's begin by inserting some rectangles. And let's begin with the right approximation rectangles. So let's insert a couple of rectangles. We're going to start off here at the origin, and we're going to go out to our first value of 2, and then we're going to go up, and we're going to let the 2 dictate the height. So f of 2 Okay, so there we go. here's my two rectangles, and already we can visually see that this is going to be a much better approximation. I'm going to say that if I figure out the area of these two rectangles, the summation of these two rectangles will make a pretty good approximation of the real area we're interested in, that gray area there. Okay, so let's write down the equation then for the rightmost approximation. So that means that R sub 2, right? The R meaning that I'm going to use the right endpoints. If you think about the base of each rectangle, I go to the far right end of each rectangle, and then that is going to establish the height of the rectangle. So for this one, this is f of 2. F of 2 is that guy right there. And then up here, this guy is going to be the f of 4. Right? In each case, the 2 and the 4 represent the right edge of each rectangle. Okay, so now r sub 2, well, that's going to be equal to the width of the rectangle times the height of the rectangle. And that first one, well, that's going to be f of 2 plus the second rectangle. Well, again, it's got a width of delta x, and then we multiply that by its height. That's going to be f of 4. Okay, so this is rectangle 1 and rectangle 2, a height of f of 2, a height of f sub 4. Okay, so r sub 2 then is going to be equal to delta x, and again, just to establish the pattern, I'm going to write it down. It's going to be 4 minus 0 divided by 2 times f of 2. Now f of 2 is 2 squared plus 1 plus delta x, which is again 4 minus 0 divided by 2 times f of 4, which is again 4 squared plus 1. So r of 2 is equal to 2, right? The base of each rectangle is a width of 2. And then the height is going to be 4 plus 1 is 5. So 2 times 5 is going to be the area of that first red rectangle. Plus, and now this is going to be 2 times, and then 4 squared plus 1 is going to be 17. So r sub 2 is equal to 10 plus 34. So r sub 2 is equal to 44. Okay, well, likewise, we want to approximate it using the left endpoints. So let's insert some rectangles. Let's go back with green rectangles. And we want to put rectangles that have the same base. Start off there. So they're going to have the same base up to there. But this time the height is going to be established by the left side. Okay, so there's my two green rectangles. Let me fill them in a little bit. So now we want to find the area of these green rectangles, and they will also represent a pretty good guess about that gray region. So let's write this down. So L sub 2, remember L represents now that with each rectangle, we're going to use the left edge of the base, right? Looking at the base of each rectangle. Now we're going to use the left edge to establish the height. So for the first rectangle, the height is going to be established at f of 0. And for the second rectangle, the height is going to be established using this point, which is f of 2. Okay, so let's write that down. So r sub 2 is equal to delta x times f of 0 plus delta x times f of 2. So L sub 2 equals to delta x, which is again 4 minus 0 divided by 2, times, this time this is 0 squared plus 1 plus 4 minus 0 divided by 2 times 2 squared plus 1. 0 squared plus 1 is just 1, and then 4 divided by 2 is 2. So L sub 2 is equal to 2 times 1 plus 2 times, and then this is 4 plus 1 is 5. So L sub 2 is equal to 2 plus 10, which is 12. Okay, so clearly the green one is an underestimate, right? The gray area is definitely bigger than the sum of the two green rectangles. And clearly the red rectangles is an overestimate. The gray area is somewhere in between the two. So we can again say that the real area we're interested in, the real area, is less than r sub 2, but greater than L sub 2. It's somewhere in the middle there. But we're getting closer. Earlier, we were able to trap it between, let's come back up here. Earlier, we were able to trap the area to be somewhere between 4 and 68 using L1 and R1. But now we can get an even better approximation and say that the area must be somewhere between 12 and 44. 12 less than the area less than 44. So we're squeezing in on it from both directions. And that's just with two rectangles. All right, let's get really serious about this. Let's do 4 rectangles. Okay, so this time we want to let delta x go from 4 minus 0 divided by 4, since we're going to do 4 rectangles. Which clearly means that each rectangle is a width of 1. So we're going to go from x goes from 0 at 1, at 2, at 3, and at 4. And we're going to have rectangles. Okay, so let me draw in the rightmost rectangles. Okay, so there are my 4 approximating rectangles. In each case, I used the right rule, right? So if you think about the base of each rectangle, the base has got a delta x. So let me draw them in here. Each one of these little bases is a delta x, which in this case is equal to 1. Delta x there, this width there is delta x. So each rectangle is going to have a base of delta x. And the height is going to be based on using the right edge of each base, the right side edge. So for the first rectangle, it's going to be this point right here, which is going to be f of 1. F of 1 is that point right there. And then for the second rectangle, we're going to use f of 2, which is that point right there, height of f of 2. And then for the third rectangle, we're going to use f of 3, which is going to be that point right there. And then finally, for the last point, we're going to let that be equal to f of 4. F of 4. Okay, so let's write down the formula then. So r sub 4, right, using the capital R means that we're using the right side edge of each base of each rectangle. And the little subscript 4 means that we're using 4 rectangles. Okay, so it's equal to the sum of 4 rectangles. Each rectangle is going to have a base of delta x. So it's going to be delta x times f of 1 for that first one, plus delta x times f of 2, plus delta x of f of 3, plus delta x of f of 4. Okay, so r sub 4 is equal to delta x, which is equal to 4 minus 0 divided by 4, times f of 1, which is 1 squared plus 1, plus another 4 minus 0 divided by 4, times 2 squared plus 1, plus another 4 minus 0 divided by 4, times 3 squared plus 1, plus 4 minus 0 divided by 4 times 4 squared plus 1. Good. So all these 4 minus 0 divided by 4s, they're all going to be equal to 1, so we can simplify those really easy. It's going to be 1 times, and then 1 squared plus 1, that's 2, plus 1 times, and then this is 4 squared plus 1, that's 5, 1 times 5, plus, and then this is going to be 1 times, and then 9 plus 1 is 10. 1 times 10. Plus, and then 1 times, and then 16 plus 1 is 17. 1 times 17. So r sub 4 is 2 plus 5 makes it 7. 17 plus 17 equals to 34. So there's the sum of all 4 red rectangles equals to 34. Okay, now let's figure out the left side one. Let me insert all those left side rectangles. Okay, so L sub 4 is equal to delta x times f of. Now we're using the left edge for each rectangle. So for this very first rectangle, the left edge is 0. So we're going to use f of 0 for that first one. F of 0, right there, f of 0. So this represents the area of that first green rectangle, plus delta x times f of 1, right? For the second rectangle, the left edge is a 1, plus the third rectangle, f of 2, plus the fourth rectangle, which is f of 3. Okay, so L sub 4 is again equal to 4 minus 0 divided by 4 times 0 squared plus 1, plus another 4 minus 0 divided by 4 times 1 squared plus 1. 1 squared plus 1, plus 4 minus 0 divided by 4 times 2 squared plus 1, plus another 4 minus 0 divided by 4 times 3 squared plus 1. So we get that L sub 4 is approximately 1 times 1 plus 1 times 2 plus 1 times 5 plus 1 times 10. Or L sub 4 is equal to 1 plus 2 makes it 3, plus 5 makes it 8, plus 10 makes it 18. So there's our approximation for L sub 4. So we can establish that we think that the real answer, the real area, is less than 34, but greater than 18, right? Clearly the gray area that we're after, the real answer, is going to be bigger than the sum of the green rectangles, which was the 18, but smaller than the sum of the red rectangles, which is the 34. So we're getting a better approximation of area. Okay, so this 18 was the L sub 4, the area, and then the 34 was this R sub 4, right? And the real answer is somewhere in between the two. But either one by themselves makes an okay approximation. Clearly not great, but we're getting closer and closer to the real answer. Okay, so let's step back and take a look at the 3 that we've done so far. We started out with approximating the area with one rectangle, and we found that with one rectangle, the L sub 1 value was 4, the R sub 1 value was 68. So we found that the area, the real area, is somewhere between 4 and 68. Let me highlight that. All right, we found the area was there. Good. Okay. Next, we stepped up our approximations and said let's use 2 rectangles. So we found R sub 2, 2 rectangles using the right edge, R sub 2. And we found that the sum of those 2 rectangles was 44 units. And then we also found L sub 2, the 2 rectangles where we used the left side of each base of the rectangle to establish its height. So we found that that was 12. So then we found a better approximation for the real area. The real area is somewhere between 12 and 44 when we used 2 rectangles. Then we stepped it up even more and used 4 rectangles. So R sub 4 we calculated to be 34, the sum of the 4 red rectangles. And then we found L sub 4, the green rectangles, and that equaled 18. So now we had an area that we discovered that the real area we're interested in is somewhere between 18 and 34. Okay, so each time when we increase the number of rectangles, we get closer and closer to the actual area. We get an interval that gets smaller and smaller. We're squeezing in from both sides. We're getting closer and closer to finding the real answer. Let's use technology to confirm all the work that I've done here. Okay, back to this online applet at this address here. I typed in my equation, x squared plus 1. Here it is, right? This parabola is the equation, y equals to x squared plus 1. And I'm interested in this gray shaded region here. So the first thing I did is I approximated using one giant rectangle where we use the rule of using the right edge to establish the height. So that would look something like this. One giant rectangle like this. I colored it in red earlier, but here it's in yellow. Okay, and if you note right over here, it tells me what that area is, 68. When we calculated it by hand, we determined that it was 68. Okay, so that was R sub 1. We also used the rule of using the left edge, so we can also find L sub 1. So the left endpoint rule is this one, and that would be this red one here. And just like we did when we did it by hand, L sub 1 is equal to 4. So we found that the real area is somewhere between 4 and 68. Okay, then we stepped it up and said, okay, well, not just one rectangle. How about if we had two rectangles? Just like that. So here is the right edge ones. So going out to the right, first rectangle, the rightmost edge goes up to there. So we had a height of 5. The second rectangle, using the right edge, goes up to 4, which goes all the way up to there, up to 17. And so the sum of those two rectangles is equal to 44, just like we figured out when we did it by hand. And then we can also use the left end rule, and that would be these red ones. So this first rectangle, we use the left edge, which is 0. Evaluate our function at 0, and then that gives you that height. And we also use the left edge of this rectangle. Looking at its base, the left edge goes up to a height of 5. Then we find those two, and we find L sub 2. So L sub 2 is equal to 12, just like we had found before. And R sub 2 is equal to 44. So now we know that the real area is somewhere between 12 and 44. Okay, and then we can step it up some more. We went up to 4. So here it is with 4. Focusing on the right edge, here are 4 rectangles. And the sum of those 4 rectangles is 34, just like we had found before. And we can also use the same idea to find the L sub 4 value, which is equal to 18. Okay, so this confirms all the work we've done, but as you've probably noticed, it's not fun doing these things by hand. So it's nice to have technology to step it up even further. So let me focus on just the right edge one for a minute. What we want to do, as you might imagine, is continue to add more and more rectangles. When I had just one rectangle back here, that was a terrible approximation. One giant rectangle like that, it was a bad approximation of that gray region, right? But with 2 rectangles, it got a little bit better. With 4 rectangles, it got even better. Well, guess what? It's going to get even better if we use 5 rectangles, or 6, or 7, or 8, or 9, 10, right? So as we increase the number of rectangles to more and more and more rectangles, say we go all the way up to 50. Okay, so when n equals to 50, there are 50 rectangles here, all of them using the right end rule. And as you can see, the sum of all 50 rectangles will now give us a very, very nice approximation of the true area underneath the curvature. Of course, it's not perfect. If we zoom in, let's zoom in right in here, we see that in fact, we still have an overestimation. right? Each rectangle is still a little bit above the blue line, so there's always going to be a little extra area that we're counting that we shouldn't be counting. So this is still going to be a slight overestimation, but it will be a much better estimation than back when we were only using 1, 2, 3, or 4 rectangles. Likewise, if we focus on the left-hand one, back when we only had 1 rectangle, that's a severe underestimation, right? The area of this red shaded rectangle is way smaller than that gray area. And then as we go up to 2 rectangles, to 4 rectangles, and then we start bringing it up to 5, 6, 7, 8, 9, 10, we see that slowly but surely the sum of all of those red rectangles get really, really close to the real answer. So if we go all the way up to 50, we start to see that that becomes a really nice approximation. Again, if we zoom in though, we see that in fact there's always a little bit of a gap though. There's always a bit of an underestimation. Every single rectangle is a little bit lower, always has a little bit of space in gray that wasn't counted. So the sum of all those red ones is still going to end up being a slight underestimation from the real answer. But as we can see visually here, it becomes a really, really nice approximation. Okay, so you can see that calculating these things would be a real pain. It was pretty painful to do it even with 4 rectangles. Doing it with 50 rectangles would be messy. So what we want to do is we want to establish a general pattern where we establish a formula using n rectangles. And then we're going to let the number of rectangles n go out to infinity, because an even better approximation than 50 rectangles would be 100 rectangles or 1,000 rectangles or 10,000 rectangles. Can you imagine how precise, how good an approximation this would be if instead of 50 rectangles, we use 50,000 rectangles? Or how about 50 million rectangles, right? So if we push the number of rectangles out to infinity, we will get an infinitely good approximation to the area we're interested in. Okay, so we want to set up a formula that involves n number of rectangles, and then we want to use our knowledge from limits to push that out to find the limit as n goes out to infinity. Hopefully that limit exists, and if we can find that limit, then that would be an infinitely great approximation for the area underneath the curvature. Okay, so back to our parabola and finding the area underneath it. Remember that this curvature then is the curve y equals to x squared plus 1. That would be that curve right there. When we find that area in gray, this reaches all the way out to 4. And then this comes out, this is 0 there. Okay, so we want to just establish a pattern for n rectangles. So let's think about the base first. I'm going to go ahead and kind of focus on this part here. So I'm going to kind of zoom into it. Okay, so this just is a zoomed out, expanded portion of this right here. So we can kind of write on it here. Okay, so over here. So first of all, there's going to be lots of rectangles coming up, right? So let's think about the base of those rectangles. We're going to start off at 0. So this will be 0 there. And then the next rectangle will have a base that goes out to there, and then 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 out to there, and dot, 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 so on and so forth. At the very end, the base of those rectangles will come out to here like this, right, all the way out to there. How big are those bases going to be? That's what delta x is. Delta x is the base of each rectangle, and it's equal to 4 minus 0 divided by the number of rectangles. And so in this case, it's just going to be equal to 4n. That's the width of each one of these rectangles. So this little width of this rectangle right here, that's delta x. And the width of this little rectangle, well, that's also delta x, right? Each one of these widths from the beginning all the way out to the end is a delta x. And they all equal a width of 4 divided by n. Okay, so then let's label this one here as x sub 1, and this point as x sub 2, and this one as x sub 3, and so on and so forth, which means that that first one there, the 0, should be x sub 0. Okay, going out, so then 1, 2, 3, 4, dot, 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 all the way out. So then we'll end up with n of them. So this guy out here ends up being as x sub n. The one that came right before it, by the way, then would be x sub n minus 1. Good. Now let's establish a pattern for what those values actually are. So x sub 0, well, that's just 0. And then x sub 1, well, that's going to be the 0 plus the delta x. So one copy of delta x, which is this 4 over n. X sub 2 is equal to the 0 plus, and now there's 2 copies of the delta x, which is 4 over n, right? So thinking about what this value is here, the x sub 4, it comes out to here. Let me make some space here. Goes out to there, and that distance right there, well, there's 2 copies of delta x. 2 times delta x is equal to x sub 2. That's a nice pattern. And now the third one, well, then there's 3 delta x's to get to the third one. So x sub 3 is going to be equal to 0 plus 3 times 4 over n, and so on and so forth. And so the very last one, x sub n, is equal to 0 plus, and looking at the pattern, the subscript there matches with how many multiples of the delta x's. So the last one should be n times the 4 over n, which makes sense because then the n's cancel to give you that the x sub n is equal to 4, right? Which is what we have here. X sub n equals 4. Okay, in order to establish a general pattern, we need to think about somewhere in the middle. Somewhere in the center, there is an ith one. Okay, so as we keep going through this pattern, somewhere, let's say somewhere around here, we arrive at the x sub ith one. And the one right before it, and I'm going to make it a little bit bigger so we can have space to write, but you got to imagine that they're really close together. But I'm just going to write them down a little bit more spaced apart. This one, the one that came right before it, would be the x sub ith minus 1. Now, how wide is the width there? Well, the same as everywhere else. It's a delta x. Good. And establishing the same pattern as before, then, as we keep going, we see that the x sub ith one, let me erase this, the x sub ith one is equal to 0 plus I times 4 over n. There are I number of delta x's from there all the way out to there, right? When we had x sub 1, there was 1 delta x. When you had x sub 2, there were 2 delta x's. Then 3 delta x's, 4 delta x's, so on and so forth. So when we get to the x sub ith one, there are I multiples of delta x to the left of it. Good? Okay, so that's what that means. And then the one that came right before it, if we need it, let's just write it down. minus 1, well, following the same pattern, it would be 0 plus, and then it would be I minus 1 times 4 over n. Okay, so following this pattern, we get to the x sub I minus 1, then the x sub I value, and then if we keep going, we go all the way out to x sub n. Now, very conveniently, I've chosen this problem very carefully to start off at 0, just because for this first problem, it makes things work out really nicely, since 0 plus anything is just going to be that value. So we could just completely ignore the zeros here and simplify this a little bit, and we see that this can be simplified to say that x sub 0 is just 0, and then x sub 1, well, that's just going to be equal to 4 divided by n, and x sub 2, scroll over here, well, I'm just going to, I could write it as 8 over n, but for the purposes of what we need right now, I'm just going to leave it as 2 times 4 over n. And then dot, 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 and then the ith one, x sub I, is equal to I times 4. Don't confuse this with imaginary numbers. It's not an imaginary number. It's an index over n. And then dot, 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 dot. And again, just to establish the pattern, x sub n is equal to n times 4 over n. Okay, so those are all the values along the horizontal axes. And then as we imagine all of those values here, right, so this is just a zoomed in version of this, we imagine that there's going to be rectangles up here. So I'm just going to draw in one rectangle, right? I can't draw in n rectangles, but I can draw one of them, and you can imagine what the other ones kind of look like. So let's put in the nth rectangle. Okay, so I'm using the right end rule. So that point right there will come from plugging in this point, which is the x sub ith value. And then so this point up here would be the f of x sub ith value. F of x sub ith value would be that one right there. And then, of course, we're interested in finding out the sum of all these rectangles as an approximation. So let's write down the formula. So r sub n is going to be equal to the first rectangle, which is going to be that width of delta x. They all have a width of delta x, times f of x sub 1, right? Remember that that first rectangle is this, and if we think about, let me highlight it, this first rectangle is going to be this guy right here, and if we're using the right end rule, then the height of the first rectangle is going to be determined by plugging in x sub 1 into that rectangle. So the first rectangle is going to be this product, delta x times f of x sub 1. The second rectangle is going to be delta x f of x sub 2 plus dot, 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 dot. Let's get to that middle value. That middle rectangle is still going to have a width of delta x times f of x sub I plus dot, 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 plus all the way out to that last final rectangle. And that final rectangle is going to have still a width of delta x, and it's going to have a height determined by f of x sub n. Good. We can factor out a delta x from all of them. They all have a delta x. So this r sub n formula becomes delta x parentheses f of x sub 1 plus f of x sub 2 plus dot, 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 plus f of x sub I plus dot, 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 f of x sub n. Good. All right, so now that r sub n formula becomes delta x times, okay, f evaluated at x sub 1. So this becomes x sub 1 squared plus 1 plus x sub 2 squared plus 1 plus dot 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 dot. The ith one becomes x sub I squared plus 1 plus dot 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 plus x sub n squared plus 1. Good. And as we see right here, the delta x, that's equal to 4 over n. I'm just going to replace that here. This is 4 over n times. Now x sub 1, we have these little patterns over here. X sub 1 is equal to 4 over n. X sub 2 is 2 multiples of the delta x. So that was 2 times 4 over n, and so on and so forth. So this becomes 4 over n squared plus 1 plus 2 times 4 over n squared plus 1 You know what? It's getting a little confusing here, so let's make sure we put parentheses there, and then there is parentheses here, and then there is parentheses here, plus dot 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 all the way out to the ith one. Okay, so the x sub ith one, again following our little pattern, is over here. It's 4i over n. So this is going to be 4i over n, and then the whole thing gets squared, and then we add 1 to it. That's the result we get there. Plus dot 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 dot, and then that last one over there, that becomes the nth one. That would be 4n over n. So this becomes 4n over n squared plus 1. And then we close that out, and then all of that gets multiplied by this 4 over n. Okay, all right, so let's further simplify. Remember, all of this gets multiplied. Let's put it in red. The 4 over n gets multiplied by the whole thing. Let me erase this for now. And continue to simplify this. So as you can see, all of these parentheses here in blue, they all share a 4 over n squared in common. 4 over n squared, 4 over n squared, 4 over n squared. So we can simplify this to be 4 over n, and then a giant red bracket. And then I can factor out of all of these blue parentheses a 4 over n squared. So I'm going to factor out a 4 over n squared. So I'm just going to write it like this, squared. And then parentheses. So for this term, it'll still be a 1 plus 1. I'll write 1 squared plus 1 so we can see the pattern. Plus, now in this bracket, oh, no, that's not true. Okay, so now I'm going to continue to simplify this a little bit. We'll get r sub n equals to 4 over n, and then there's this giant red bracket. And then inside each one of these blue parentheses, I'm going to separate these a little bit the following way. So I'll leave the first one alone. So that's just going to be 4 over n parentheses squared plus 1. Plus, and now this one I'm going to separate as 2 squared times 4 over n squared plus 1 plus dot 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 dot. The ith one is going to have I squared. Remember, it's not an imaginary number, so that has nothing to do with that. It's just the index I squared times 4 over n squared plus 1 plus dot 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 dot, and then that last one is going to have a n squared times 4 over n parentheses squared plus 1. And then again, close off this giant red bracket. Okay, so now I'm just going to reorganize these. There's all these 1's running around. Plus 1 there, plus 1 there, dot, 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 plus 1 there, plus 1 there. So I'm just going to put them at the end and regroup all of these. So this would be equal to r sub n equals to 4 over n, giant red bracket, and I'll write down 4 over n squared plus 2 squared times 4 over n squared plus dot 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 plus I squared 4 over n squared plus dot 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 plus, and then this term, n squared 4 over n squared plus, and now we had all these 1's running around. There was a plus 1, plus another 1, plus another 1, plus another 1. And how many 1's would we have? Well, there were n of them. So that's how we're able to simplify that. So plus like that. And now all of these, I'm going to group them all up. The sum of all of these right here, I'll highlight them in yellow. The sum of all of those is just going to be n. 1 plus 1 plus 1, and there are n of them, so all of that just adds up to n. Okay, so let me rewrite this up here. R sub n is going to be equal to 4 divided by n times this giant bracket, and then the pattern is 4 over n squared plus 2 squared times 4 over n squared plus dot 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 plus the ith one, which is I squared 4 over n squared plus dot dot dot, then all the way out to the nth one plus n squared 4 over n squared plus, and then we just established that at the end there will be a plus n. And close the giant red bracket. Okay. All right, well, as you can see, the first few terms, the first n of these guys, they all share this 4 over n squared pattern. And just to make the pattern fit nicely, I'm going to insert a 1 squared in front. 1 squared. Because we see that there's a 1 squared there, 2 squared there, dot, 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 ith squared, dot, 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 all the way out to n squared. So this r sub n is going to be equal to 4 over n times, and then again this giant red bracket, where factoring out a 4 over n squared times, and then there'll be this pattern of 1 squared plus 2 squared plus 3 squared, 4 squared, dot, 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 all the way out until the ith squared, plus dot, 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 all the way out to the nth squared, plus n, and then we end this bracket there. Okay, ugly. Now we're going to distribute this 4 over n times this term and then that term, right? So the 4n multiplies times these two, the product of these two, and then the 4 over n multiplies times that term over there. So we get that r sub n is then equal to 4 over n times 4 over n parentheses squared times this pattern of 1 squared plus 2 squared plus 3 squared plus 4 squared dot 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 plus ith squared, this ith one, plus dot 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 all the way out to the nth squared, plus, and then at the end here we have a 4 over n times n. Okay, so clearly these two simplify, so we just have a plus 4 at the end. And then here we can combine those and get that r sub n is equal to the formula 4 to the power of 3 divided by n to the power of 3 times this, this ends here, which is 1 squared plus 2 squared plus dot 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 all the way out to the ith squared plus dot 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 all the way out to the nth squared, that's where it ends, and there's a plus 4 at the end. Okay, so now at this point, I'm going to need an assist to help me simplify this portion of it. Luckily, this is a formula that hopefully is familiar to you. So hopefully in your pre-calculus class, in the proofs by induction, you ran into something that looks like this. The sum of this pattern, so 1 squared plus 2 squared plus 3 squared dot 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 all the way out to n squared. This sum can be proved to be equal to this, n times n plus 1 times 2n plus 1, all of it divided by 6. So this is what we're going to use. Okay, so I'm going to replace this portion of it with this equation in our little statement above. Okay, so n times, I'm going to use that and bring it up here. And this highlighted yellow part is going to be replaced by that formula. So now then we have that r sub n is equal to 4 cubed over n cubed times, and now that is replaced by this formula, which is equal to n times n plus 1 times 2n plus 1 all over 6, and then there's this plus 4 out here. Okay, and now we can reduce one of these n's. This one reduces to 2 and cancels with that one. And then I'm just going to put that constant and bring it out here. So we have that r sub n is equal to 4 to the power of 3 divided by 6 times n plus 1 times 2n plus 1 divided by n squared. And then there's this plus 4 over there. Okay, so now we have a formula for the sum of n rectangles using the right rule. Okay, that's what this is. And what we want to do now is think about what happens as we let the limit of n go to infinity. So the limit as n goes to infinity of r sub n is equal to the limit as n goes to infinity of this formula to the third over 6. That's a 6, by the way. And I'm going to separate this into two pieces. So this will be times n plus 1 divided by n times 2n plus 1 divided by n. And then the limit as n goes to infinity of 4, well, that's just going to be 4, right? It doesn't get affected by it. So I'll just put a plus 4 out here. And then the limit as n goes to infinity of these two, well, let's do one more step to simplify it. This is going to be the limit as n goes to infinity of, well, actually, let's factor out this constant. And we'll get 4 to the third power divided by 6 times the limit as n goes to infinity. N goes to infinity of this first fraction, which I'm going to rewrite as 1 plus 1 over n, dividing these, times the limit as n goes to infinity, and then dividing n here as well, we get 2 plus 1 over n, right? So all of these are being multiplied. So it's this whole thing times this whole thing. And then there's a plus 4 here. Plus 4. Okay, so now when we apply the limit as n goes to infinity, this goes out to 0, and this goes out to 0. So we really just end up with a 1 here and a 2 there. And so we get that limit equals to 4 to the third divided by 6 times 1 times 2 plus 4. Okay. So reducing this gets us to a 3 there. So we get 4 to the third power, which is 64. Let me zoom out a little bit. Which will be equal to 64 divided by 3 plus 4. Get a common denominator of 3 over 3. And that'll be 12 over 3, which will then give me a 76 divided by 3. And that is the limit as n approaches to infinity of r sub n equals 73 divided by 3. And if we turn it into a decimal, that'll be 25 and 1/3 as a mixed number, which means it's 25.333333 is the answer we get. Okay, let's recap real quick here. We want to find the area of this gray region, right? So what we did was we established a rule that described the sum of n rectangles. Okay, so we broke up the horizontal axes from 0 to 4 so that there are n rectangles. The width of each rectangle is the width of each rectangle is equal to 4 minus 0 divided by n, or just 4n. 4 over n is the width of each rectangle. They're all the same width. And then if we focus on that middle one, somewhere in the middle there's the ith rectangle. And so this one that I drew is the ith rectangle amongst the sea of n rectangles. This is the ith one somewhere in the middle. And so we keep track of that to help us with our patterns. Okay, so r sub n is equal to this product here, delta x times f of x sub 1 times delta x times f of x sub 2, so on and so forth. So there are n products here, n terms in this summation, and each term is a product of a base, all the bases are delta x, times a height, which is f of, and then we need to pick a particular value. We're using the right n rule, so following the pattern, we see that the first one's x sub 1, x sub 2, dot, 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 all the way out to x sub n. Okay, so we continue to simplify, cancel, reduce, combine, do our algebra magic to simplify life here. And this moves on to here. We get to this point. We took an assist from our pre-calculus class to see that this sum equals this formula. And so we ended up with a nice formula for r sub n. This formula is a formula such that if I choose the number of rectangles and plug it in here, it'll tell me the results. So Earlier, we figured out what it was when it was, say, 1 rectangle, 2 rectangles, 3 rectangles. Let's confirm we get the same answer. Let's see what happens when we plug in 2. So, for example, r sub 2, when there are 2 rectangles, that would be 4 to the third power divided by 6 times 2 plus 1 times 2 times 2 plus 1 all over 2 squared plus 4. Good. This is when n equals to 2. N equals to 2, n equals to 2. So we get that r sub 2 equals to 64 divided by 6 times 3 times 4 plus 1 is 5. 5 divided by 4 plus 4. So stuff reduces a little bit. 3 reduces with that to give me a 2. 2 reduces with 64 to give me a 32. 4 goes into 32 8 times. And so we get 8 times 5 is 40, 44. R sub 2 is equal to 44. See? So this formula automatically gives me the sum of the n number of rectangles using the right rule. Okay? So 44 is what we got before when we did it the long way. Okay, so now that we have a formula for the sum of n n rectangles using the right n rule, now what we want to do is find the limit as n goes to infinity of r sub n. Right, so this is supposed to be all the same. I just got a little lazy here. On this side, it's all same. So the limit as n goes to infinity of r sub n equals this formula, and then equals this formula, equals this formula. We were able to see how we can manipulate it, and ultimately we got to 25.33. And so this is the exact answer to the area underneath the curvature. The gray area that we were after is exactly 25.33 units. So the gray area that we were after is now exactly equal to 25.33. When we had a formula of r sub n, we can get an approximation. The bigger the n value, the better the approximation, but it was always an approximation. But now when we let n go out to infinity, we get an infinitely close approximation. In fact, it's the exact answer. So now we no longer say that this is an approximation. This is the exact answer. Right? Because n is going out to infinity. There's an infinite number of rectangles that are being summed up, and the sum of all those infinite rectangles is equal to 25.33, which is the area of that gray region that we were after. Okay, so now let's validate all this work, again using that free online applet. Okay, so again, using this free online applet, here is that area we were interested in gray. And as you might have already noticed, the answer has been here all along. The computer automatically calculated that area to be 25.333333, right? So exactly what we determined by hand, but here just automatically calculated by the computer. Okay, and then if we keep track of the right end rule, where all the rectangles have a height determined by the rightmost point at the end of each, at the base of each rectangle, the right end point, then when we had one rectangle, we got that the approximation was 68. So this would be 4 times this height, 4 times 17, right, this is 17, is 68. So that was that first initial guess. Obviously, the answer is 25.33333, so 68 is a pretty terrible guess, but it's a place to start. And then we upped our game to 2 rectangles. With 2 rectangles, we got that area, the sum of those 2 rectangles was 44 units. Again, much higher than the 25.33, the real answer. But then we really started to create more rectangles. With 4 rectangles, we got an answer of 34, much closer to the 25.33. And then if we just keep going, keep an eye on that, the result of the right end rule approximation. So with 15 rectangles, we're already at 27.51. That's the sum of all these 15 rectangles equals to 27.51. Pretty close to the 25.33. That's the actual answer. And again, focusing on this, number, as I increase the number of rectangles, we see that they just keep getting closer and closer and closer and closer and closer. When we get to like 50 of them, we have a pretty good guess already, 25.977, when the real answer is 25.33. Okay, but we just keep going and going and going and going, and we see that as we let the number of rectangles go out to infinity, the sum of all those rectangles will get infinitely close to this number until we apply our formula for limits and let n go out to infinity. And if we can figure out what that limit is, we'll get the exact answer. No longer an approximation, but the exact answer. Okay, so now let's revisit the exact same thing, but from an even more abstract perspective. So let's say that a function is given to us, and it's simply stated as f of x, not a specific equation. So y equals to f of x. Why not represent it like this? Just this arbitrary function that kind of looks like this curvature right here. So we're going to start by subdividing S. Capital S is the area we're interested in, the entire blue shaded region. And so what we're going to do is think about breaking it up into little pieces. We've got S sub 1, S sub 2, S sub 3, so on and so forth. There are n little segments. So we start by subdividing S into n strips, S sub 1, S sub 2, S sub 3, dot, 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 all the way out to S sub n of equal width. Right? The width of the interval from a to b is b minus a, right? So think of maybe, for example, if, putting some numbers on here, if a was 3 and b ran all the way out to, say, 10, then that distance from a to b would be the distance 10 minus 3, which would be equal to 7. And that would be that distance along the base, right? So we just subtracted b minus a. And then if we want n of them of equal width, that means that each delta x would be equal to b minus a over n, right? So in this little example, if I wanted n rectangles, then each one would be delta x would be equal to 7 divided by n, 10 minus 3 divided by n. Okay, but we want to leave it abstract, so we don't want to have any specific numbers at all. We just want to say that it runs from A to B, and so this represents delta x. Delta x is the width of each rectangle. So coming back over here, that means that the width of this eventual rectangle, right? Eventually we're going to have a rectangle, is a delta x, and this one, its width is also delta x, and so on and so forth. And in particular, we're going to focus our attention on the ith rectangle. So this is delta x. So notice that following the pattern, the first rectangle it matches with this little subscript of 1 there. So the right end describes that this as the first rectangle. The second rectangle, it matches this little subscript of 2. So this is the second rectangle, the third, the fourth, the fifth. Therefore, I know that this one is going to be the ith rectangle, and it's got a delta x as its width, right? They're all equal width, delta x, going out to the very last one. This one's also delta x. And again, following the pattern for x's, if this is x sub 1, then this first one, we can refer to it as x sub naught. And then dot, 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 all the way out to the very last one. And the very last one is going to be x sub n. And x sub n is equal to b. So x sub naught equals a, x sub n equals to b. Okay, so these strips divide the interval from a to b into n subintervals. The first subinterval goes from x naught to x1. The next one goes from x sub 1 to x sub 2, and so on and so forth, right? So these intervals are referring to these right here. So the first interval is this one, and it goes from x sub naught to x sub 1. That's this first interval. And then the next interval goes from x sub 1 to x sub 2. That's this interval. and so on and so forth, right? So if we keep going dot, 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 all the way out to the last one on here, so then this interval at the end there represents the last one. So it's the interval that goes from x sub n minus 1 out to x sub n. Okay. So if we're going to be using the right endpoints rule to create our rectangles, then that means that the very first rectangle is going to have a height determined by evaluating our function at x sub 1. Right? The height of the first rectangle is going to be determined by evaluating our function at x sub 1 using the right endpoint rule. The second rectangle is going to have a height determined by x sub 2, and so on and so forth. So x sub 1 is going to be equal to a plus delta x. Right? Think about this subinterval right here. So the x sub 1 value, x sub 1 is going to be equal to a plus delta x. X sub 1 equals to a plus 1 copy of delta x, right? Because this is delta x right there. Now the x sub 2, tying it back to a, where a starts, well, that's going to be equal to a plus, and then there are 2 copies of delta x. There's a delta x plus another delta x. That's x sub 2 equals to that, which can be simplified to a plus twice delta x. And that's what this is highlighting here. The x sub 2 is equal to a plus 2 copies of delta x. The a sub 1 is equal to a plus 1 copy of delta x, and so on and so forth. And again, we establish a pattern. The third one is going to have 3 copies of delta x. So once we make it all the way out to here, x sub 3 is going to be equal to a plus 1 copy of delta x plus a second copy of delta x plus a third copy of delta x. And that's what this is. X sub 3 equals to a plus 3 delta x. Okay, so following that pattern helps us establish the following. So let's approximate the ith strip S sub I. So that refers to this one right over here. So that would be the ith strip is this one. Approximated by a rectangle with width delta x. So all the rectangles have a width of delta x. So that's what this is. Delta x, that width. And the height, using the right endpoint rule, is equal to the function evaluated at x sub I. So that's what this represents. We kind of go all the way out here. This height right here represents f of x sub I. And that gives you that height right there. Or, if you like, that ordered pair right there represents the ordered pair x sub I, comma, f of x sub I. Okay, so we're interested in identifying the area of this rectangle here, ith rectangle. Then that one by itself is delta x times f of x sub I. So this area by itself, this area is S sub I is approximated by delta x times f of x sub I. Good. So then the area of the ith rectangle is f of x sub I times delta x. What we think intuitively as the area of S is approximated by the sum of the areas of these rectangles, which is then going to be equal to this. Good. So this represents the area of the very first rectangle. As you can see from the picture, that means that it's got a base of delta x. All of them have a width, a base width of delta x. By design, we want all of these to be the same of equal width, delta x. And using the right endpoint rule, that means that the first rectangle is going to have a height determined by evaluating f of x sub 1. Good. And then the second rectangle is going to have a height determined by this point, which is f of x sub 2, and so on and so forth. And that's what this represents. So this is going to be the sum of the first n rectangles, and that gives us a formula for r sub n, right, using the right end rule. Okay, so we can see that if we let n equal to 2, we have two rectangles. Here's our approximating rectangles. The sum of these two blue rectangles gives us one approximation of the area underneath the curvature. If we use 4 rectangles, then the sum of these 4 rectangles gives us an approximation, a better approximation than before, but still not great. And then as we use 8 rectangles, we get a better approximation. As we use 12 rectangles, we get an even better approximation. So just like earlier, as n goes to infinity, we'll get better and better and better approximations. If we can figure out the limit as n goes to infinity, if that gets solved, then we'll have the exact answer. Right? So if you want a pretty good approximation, let n equal 1,000,000. 1,000,000 rectangles will give you a very nice approximation, but still not the exact answer. But if we can figure out the limit as n goes to infinity, then that will be the exact answer, if it exists. Okay, so now we have a more general definition. If we define area A as the region S, we can define the area A in region S in the following way. So the area A of a region S that lies under the graph of a continuous function f is the limit of the sum of the areas of approximating rectangles. So A equals the limit as n goes to infinity of r sub n, which is equal to the limit as n goes to infinity of this equation. And it can be proved that the limit in definition 2 always exists since we are assuming that f is continuous. It could also be shown that we get the same value if we use the left endpoints. Okay, so the only difference between this equation and this equation is that here we're using the right end rule, and here we're using the left end rule. Good. But it can be shown that they both will give you the same answer. So if you approach it from one direction or approach it from the other direction, either way, you'll end up getting the same answer, which represents the area underneath the curvature. Okay, so in fact, instead of using left endpoints or right endpoints, we can take the height of the ith rectangle to be a value of f at any number x sub I star in the ith subinterval x sub I minus 1 to x sub I. Okay, so what is this saying? So let's focus our attention on the ith rectangle. So here is the ith rectangle right there. This is the ith rectangle. At one point, we were looking at right-hand rules. So we would say, okay, let's let this determine the height of the rectangle, which would mean the rectangle would go all the way up to there. And in a different rule, we said, okay, I know, let's use the left-hand rule. So the left-hand rule would mean that this input value of x would determine the height of the rectangle. Therefore, we'd go up to right over there. So using the right-hand rule, as you can see, we would end up overestimating. Using the left-hand rule, you could see we would end up underestimating it. We could also use the midpoint rule. Let's go right in the middle and use that value. But in fact, we could use any number that's in here, and that's what this little x sub I star represents. Now, it's unfortunate that it's drawn for the ith one to look like it's somewhere in the middle. It doesn't have to be in the middle. It's somewhere in that region. So, for instance, for the first rectangle, let's go back over here to the first rectangle. Here is that first rectangle. X sub I star, x sub 1 star, the very first rectangle, right, is clearly a value that is definitely not in the middle, right? It's way over here. It's really close to A, definitely not in the middle. And then x sub 2 star, again, it looks like it's closer to the middle, but it doesn't have to be right in the middle. x sub 3 star is clearly to the right of the middle. So again, not the middle value. So it could be anything in that little subinterval. And it can be shown that as long as you choose one value from within the base of each rectangle, anywhere in that base, it doesn't have to be in the middle, it could be on the right, it could be on the left, it could be in the middle, it could be anywhere in there. As long as you make selections of the star values such that x sub 1 star is in the base of the first rectangle, x sub 2 star is in the base of the second rectangle, x sub 3 star is in the base of the third rectangle, and so forth and so on. We call these values x sub 1 star, x sub 2 star, dot, 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 all the way out to n. We call these values sample points. Sample points. So when we create approximating rectangles that all have a base of delta x, right? So they're all still going to have the same base of delta x, all the way out to ith one, base of delta x. So they all have the same base of delta x. And now we let the height of each of those rectangles be determined by some x star value for each rectangle using the sample points. So if we do that, it can be proven that we're going to end up getting the exact same answer as before. Okay, so the area is then going to be equal to the limit So in a situation like that, the area is going to be equal to the limit as n goes to infinity of f sub x sub 1 star delta x plus f of x sub 2 star delta x, and so on and so forth, all the way out to the nth rectangle, which is f of x sub n star delta x. Okay, so we often use sigma notation to simplify our equations, so we got to start getting comfortable with it. So a equals, remember that's the area, equals the limit as n goes to infinity of r sub n. So this represents the the sum of the n rectangles that partition up our area. And so here are the n rectangles. Each one of them has a base of delta x. Remember that delta x is equal to b minus a divided by n. And then we can use sigma notation to simplify this just a little bit. We can also say that a equals to the limit as n goes to infinity. And then we're going to do a Riemann sum, and I want to express this so that it'll go from, let's use an index of I, goes from 1 to n of f of x sub I delta x. Right? So I just replaced all of these little numbers, 1, 2, 3, 4, dot, 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 all the way out to n, and I replaced it with I, and so now I goes from 1 to n, and this Riemann sum notation means that we're going to be adding them all. So this is area as determined by using the right end rule. Right? So for every single rectangle, we determine the height using the rightmost point within the base of that rectangle. Likewise, we can do the same thing with the left end rule. So a equals to the limit as n goes to infinity of L sub n. So there are n rectangles using the left rule. The height of each rectangle is determined by using the leftmost point in the base of that rectangle. And so we determined that this was the formula for it. And again, we can use sigma notation to simplify this just a little bit and say that the area is equal to the limit as n goes to infinity of Riemann sum as I goes from 1 to n. And so if we just keep track of this thing, it's going to be f of x sub I minus 1 times delta x, right? And notice, make sure that the pattern matches. If I replace I with 1 right here, we get 1 minus 1, which will give me that 0, that first one. And then when I put 2, I get 2 minus 1, which is 1. I'll get the second one, and so on and so forth. And then when I reach my endpoint of I equals to n, I end up with x sub n minus 1, which is the very last one in our value. Okay. And similarly, we worked with this formula. So this formula, when you see the little star, it means that we don't have a particular rule for establishing the height of the rectangle. We don't have the left rule, we don't have the right rule, we don't have the midpoint rule. We're just saying x sub star, x sub I star represents some value within the base of each rectangle. Okay, so once again, we can say that the area is equal to the limit as n goes to infinity of the Riemann sum as I goes from 1 to n of f sub x star sub I delta x, right? Again, this little index here is going to count from 1, 2, 3, 4, 5, and we see that it'll match these numbers ending at n, which matches with that guy right there. Okay, so that means that here they are. The area is equal to the limit as n goes to infinity of this Riemann sum determined by using the right n rule. And then this one is the area equals the limit as n goes to infinity. This one was determined by using the left n rule. And then finally we have sample points, where we don't necessarily have the left n rule or the right n rule or a midpoint rule. We just say let x sub I star represent any number in the ith interval, the ith subinterval. All right, now let's take a look at something called the distance problem. So now let's consider the distance problem. Find the distance traveled by an object during a certain time period if the velocity of the object is known at all times. So if the velocity remains constant, then the distance problem is easy to solve by means of the formula that the distance equals to the velocity times time, right? Meaning that if I just simply had a very simple word problem where I said a car is traveling, at 60 miles per hour, and they travel for 3 hours, how far did they go? Well, that's really easy. The distance is just going to be equal to 60 times 3. The distance is just equal to 180 miles, right? Super easy problem if the velocity is constant. But what if the velocity varies, right? If the velocity varies, it changes. You're speeding up, you're slowing down, you're speeding up, you're slowing down. Then it's not quite as straightforward, but it's also not that bad either. So for example, suppose that the odometer on our car is broken and we want to estimate the distance driven over a 30-second time interval. Okay, so the odometer is the gauge in your car that tells you how far you've traveled. Don't confuse it with the speedometer. The speedometer tells you how fast you're traveling. So we can tell how fast you're traveling, the speedometer is working, but the odometer, which tells you how far you have traveled in total, that thing is broken. Okay, so a distance traveled in 30 seconds. So what we could do is take note of the velocities that we read from our dashboard. So if we look at the speedometer readings at every 5-second intervals, right? So time 0, we look and we're traveling at 17 miles per hour. 5 seconds later, we're traveling at 21 miles per hour. 10 seconds later. So the interval in between each of these is every 5 seconds. And we see the various speeds that we get in miles per hour. Now we're looking at time in terms of seconds, and then the velocity is always given in terms of miles per hour. And we need those units to match. So we're going to do some unit conversions here. 1 mile per hour, right? There is 5,280 feet in 1 mile. And there are 3,600 seconds in 1 hour. So we can use this conversion factor to convert the velocities from miles per hour to feet per second. And that makes it match a little bit better. So equivalently, instead of seeing 17 miles per hour, we're traveling at 25 feet per second. And then at timestamp 5, we're traveling at 31 feet per second, 35 feet per second, and so on and so forth. Okay, so we have this table that describes velocities and timestamps. The interval in between each one of these is 5 seconds. So during the first 5 seconds, the velocity doesn't change very much, right? You can't really change your speed that dramatically in 5 seconds. So we can estimate that the distance traveled during that time by assuming that the velocity is constant. If we take the velocity during that time interval to be the initial velocity of 25 feet per second, then we obtain an approximate distance traveled during the first 5 seconds to be 25 feet per second times 5 seconds. It looks like you traveled a total of 125 feet in those first 5 seconds. Similarly, during the second time interval, velocity is approximately constant, and we can take it to be the velocity when t equals to 5 seconds. So our estimate for the distance traveled from timestamp 5 seconds to timestamp 10 seconds is 31 feet per second times 5, which is 155 feet. So if we add similar estimates for the other time intervals, we obtain the total distance traveled, right? During the first interval of 5 seconds, the second interval of 5 seconds, the third, the fourth, the fifth, and so on and so forth. We multiply them all separately, add them together, we get to an estimate of 1,130 feet. We could just as well have used the velocity at the end of each time interval, right? So matching it to what we were doing before, these all represent left-hand approximation points. But we could have used right-hand ones. So our first timestamp, we could have used 31 times 5, then 35 times 5, and so on and so forth to reach an estimate of 1,210 feet. If we wanted a more accurate estimate, we could have taken the velocity readings every 2 seconds, or every second, or every half a second, or every 1/10 of a second, and so on and so forth, make the intervals smaller and smaller and smaller, which means that we would have more and more accuracy. Right? This is very similar to what we've just been doing. So in general, suppose an object moves with velocity v equal to f of t, where t is a value between a and b, and f of t is definitely greater than or equal to 0. So the object always moves in a positive direction. We take velocity readings at timestamps t sub naught equal to a, t sub 1, t sub 2, all the way out to t sub n, which equals to b, so that the velocity is approximately constant at each subinterval. If these times are equally spaced, then the time between the consecutive readings is delta t equals to b minus a over n. During the first time interval, velocity is approximately f of t sub naught, and so the distance traveled is approximately f of t sub naught times delta t. This is exactly what we've been working with. We're just putting a different context to it. Similarly, the distance traveled during the second time interval is f of t sub 1 delta t, and the total distance traveled during the time interval from a to b is approximately equal to this summation. Looks familiar. So this is similar to what we achieved earlier using left endpoints. And then we can do the exact same thing using right endpoints. And so the more frequently we measure the velocities, the more accurate our estimate becomes. So it seems plausible the exact distance traveled is the limit of such an expression. So the total distance traveled equals to the limit as n goes to infinity of the Riemann sum of as I goes from 1 to n of f of t sub I minus 1 times delta t, which is equivalent to the limit as n goes to infinity of the Riemann sum as I goes from 1 to n of f of t sub I times delta t. Right? So this is the sum approximation used reaching the right endpoints, using the left endpoints for each approximating rectangle, which is exactly what we did before. Okay, so this should be more than enough to help you with your homework. Please feel free to stop by my office hours if you have any questions.